I'm Dr. Jim Zoval. You're about to watch one of my video lectures. If you like this video and would like to get videos for your entire general organic and biochemistry course, you can do so at www.zovallearning.com. I'll give you more information about that at the end of this video.
We started building a model of atoms in our head. We talked about protons, neutrons, and electrons. We're going to continue that for the first part of chapter 3 because to understand how compounds form, compounds are when you take more than one type of atom, like a water molecule, oxygen, hydrogen, right, H2O. They're what we call chemically combined. That's what we're going to learn about in chapter 3. But for us to totally understand that, what we have to do is a little bit more. We have to finish up our model of the atom. What we need to see is where those electrons are. And that's going to allow us to understand some things like this. How do fireworks work? Why that piece of paper up there that's yellow, why does that appear yellow to us? What do we want to be concerned with in this lecture today? We want to be concerned about the arrangement of electrons. Where are they? We learned about the nucleus, and we learned a little bit about electrons. We know how many electrons there are. Remember, atoms, by definition, are electrically neutral. There's total charge equals 0. The reason the total charge equals 0 is because atoms have the same number of protons and electrons. Carbon would have 6 protons. I know that because it's in box number 6 on the periodic table. That's what gives its identity, the number of protons. So a carbon atom necessarily has 6 electrons. Total charge 0, positive 6 plus negative 6 equals 0. Here's what's one of the really important educational goals for what we're going to do today is understanding where the electrons are located in the atom. And we're going to find out that where they're located correlates with the energy of that atom. So where are the electrons located, and what is the energy associated with an electron being in this particular region? When experimentalists were trying to figure out how matter was constructed and making models of atoms, they looked at the light that comes off of atoms when you put energy into atoms, either heating them up or shining light on them. What energy, what light comes out?
Energy, in the form of light or heat, can be absorbed by atoms. These videos are made to be viewed while using fill-in lecture notes. The pause in the audio is to give students time to complete the lecture notes fill-in. The lecture notes can be downloaded, free of charge, at www.zovallearning.com. Energy is absorbed by moving an electron to a new area.
So how does that work? Let's consider a simple atom. Let's consider the simplest atom, which is hydrogen. How do I know that's hydrogen? Because there's one proton, right? So if it had 2 protons, what would it be? Helium. So 1 proton, 1 electron, that's our hydrogen. Most hydrogens, the most abundant isotope doesn't have neutrons. You could have hydrogen with 1 neutron. That's called deuterium. We'll consider this. Hydrogen 1, mass number 1, just 1 proton. We have the electron moving around there. Why does that electron stay close to that nucleus? Why doesn't the electron just go flying off into space? Electrostatic attractive forces, opposite charges. There's an attraction there. That's what's holding the electron close to the nucleus. So if we were to move that electron further away from the nucleus, would it require energy to do that? Yeah, kind of like stretching a spring, right? Or pulling a rubber band, or jumping away from gravity. So if you move that electron away, let's think about the energy. So here's a bar that represents energy. Low down here's low energy, high energy. Right now the electron's fairly close to the proton, so it's a low energy. And remember, nature prefers to have everything in the lowest energy. If there's a way something can give off energy, it will do so spontaneously. That's the nature of the universe we live in. To pull that electron away requires energy. So before, this was the energy of the system. This is how much energy, this is potential energy. That's how much energy the hydrogen atom had. If you pull that electron away, You had to put energy into it. That's a higher energy. It went from low energy to high energy. Every single thing we study in this class comes back to these electrostatic forces. So how can they absorb that energy? And how do they absorb energy from light? That's what happens when put light on this, it'll absorb that energy. That energy goes into moving that electron further away from the nucleus. And we call that the excited hydrogen atom. Now, nature wants everything to be in the lowest possible energy. So if there's any way that atom could give off that energy, it will.
How do atoms give off energy? Atoms release energy when electrons move back to low energy areas. This can happen when an atom collides with another particle. Another way this can happen is by an atom emitting light. And it's this emitted light that scientists study to learn about electrons and where they're located.
How does that work? So we put energy into the matter. An electron moves further away from the nucleus. That's not a stable state. Nature would prefer it be in lowest energy, possible energy. Some things can give off energy by emitting light. That's how fireworks work. Where does the energy come from? It comes from a chemical reaction. We'll study chemical reactions in chapter 6, but some chemical reactions can produce energy. And these atoms absorb this energy. The electrons move further away from the nucleus, but then when they relax back down, they give off light and sound. Dalton's model of matter, the smallest particle, was an atom. But then that couldn't explain the pattern of light given off when we heat up matter and look at the light that comes out of it.
New scientific laws and models of nature were needed to explain the pattern of light that was emitted by atoms. To elaborate on this, I'm going to have to introduce you to a couple basic properties of light. Another word for light is electromagnetic radiation. Visible light, which is the part of the electromagnetic spectrum that can be detected with the human eye, is a small part of the electromagnetic radiation spectrum, as shown here. Light can be described in terms of waves, and when doing so, we refer to its wavelength. The different types of electromagnetic radiation are characterized by their wavelength. For example, radio waves have longer wavelengths. X-rays have shorter wavelengths. Short wavelengths correspond to higher energy. Longer wavelengths correspond to lower energy light. Now let's go back to considering the light that's emitted from excited atoms. If all energies of light could be released from excited atoms, then we'd expect the pattern of emitted light to look something like you see here. However, this is not what's observed. Only light with discrete or distinct energies is emitted. For example, the pattern of light emitted from excited hydrogen atoms is shown in the bottom of this view graph. Note that only certain colors or energies of light are emitted.
When they started making these observations and they saw only certain color, only certain energy light coming out of these excited atoms, they had to come up with a model to explain that. And all of physics at that time, right up to about 1900, was explained by the physics that Isaac Newton came up with primarily. They called it classical mechanics. Mechanics is how things work.
Our understanding of nature was dramatically changed when Max Planck and Albert Einstein introduced quantum mechanics. They proposed that energy is absorbed and emitted by atoms only in discrete amounts called quanta. Another word for discrete is distinct. Recall that the light emitted from excited atoms is generated by electrons losing energy as they move from areas further from the nucleus, high energy areas, to areas nearer the nucleus, low energy areas, as shown in this video for a hydrogen atom. The observation that only discrete energies are emitted from excited atoms is explained using an atomic model that says that the electrons can only exist in certain areas, and therefore atoms have discrete energies. We say that the energy of atoms is quantized. The first scientist to propose a model of atoms where electrons existed in specific regions that had discrete energies was Niels Bohr.
Let me give you a correlation with like a real life non-science example of something in real life that is quantized. Perhaps you guys, anyone could think of anything that's quantized that could only have certain values? Money, exactly. Because you can't get smaller, you can't have like 1.5 cents, right? So money is quantized, and the quantization unit happens to be the 1 cent in our currency. How about shoe size? When you go to the store, do you go in there and go, what size can I bring? And you go, well, I'd like why don't you bring me an 8.74? My wife hates when I do that.
Let me try to reinforce the concept of atoms having discrete energies with some visualizations. To do so, let's consider a hydrogen atom as shown in this view graph. Hydrogen 1, the most abundant isotope of hydrogen, contains just a proton and an electron. The electron is attracted to the proton through electrostatic attraction. Recall our illustration of hydrogen atom energy absorption. In that illustration, the absorption of energy corresponds to the worker pulling the electron further away from the nucleus. If a worker could pull that electron away from the nucleus and stop it at any distance, then would expect to observe any amount of energy, any color, to be emitted when the electron moves back to the low energy position close to the nucleus. Since a sample would contain millions of atoms all at various high energy positions, we would observe all colors being emitted. The emission spectra would consist of white light, and when dispersed through a prism, it would look like the visible spectrum rainbow as shown in this view graph. But as I said earlier, that's not what is observed. Only discrete colors are observed. Now you're looking at an illustration that's meant to explain discrete energy emission. When an atom's electrons are in the lowest possible energy area, we call this the ground state. At room temperature, all atoms will exist in their ground state unless temporarily excited to a higher energy area. A hydrogen atom contains only one electron and is in its ground state when that electron is in the area closest to the nucleus. As proposed by Einstein and Planck, energy is absorbed and emitted by atoms in discrete amounts. Absorption of a discrete amount of energy corresponds to the worker only being able to move to particular areas represented by red posts in this view graph. When hydrogen's electron is in any other region than the ground state region, that's its lowest energy region, we call that an excited state of hydrogen. We happen to live in a universe where everything tends to exist in the lowest energy state possible. Therefore, the excited atom will soon lose energy as the electron moves back to the ground state position. When the energy is lost in the form of light, that light will be the color or wavelength corresponding to the energy difference between the initial excited region and the final lower energy region. I'll continue this discussion of the arrangement of electrons in atoms in the next video. In that video, you'll see the shapes of the regions that electrons occupy. You can get your entire general, organic, and biochemistry course as a series of video lectures. The rental period is for 1 year, so you'll have these video lectures for the entire term of the course. You could watch the videos whenever and however many times you wish. I survey my students, and they prefer these video lectures over the textbook by a ratio of about 10 to 1. Fill-in lecture notes and an electronic version of my textbook are available free of charge at the website. To get more information or to get the videos, free textbook, and free lecture notes, visit my website at www.zovallearning.com.